4-hydroxymelion came when I worked at the Virginia Military Institute. And a colleague and I were looking at the components of a certain ant that we had just gotten from another colleague, actually on the other side of the world. And this ant had in it this compound, 4-hydroxymelion, which had never been seen in ants before, had been seen in certain types of plants, and had never been seen in insects before. And another thing was it had never been synthesized. So one of the projects I thought was trying to synthesize this compound. If you go back a little bit, 4-hydroxymelion is actually an isocoumarin, which is derived from what are called coumarins. And coumarins look like this structure here. Coumarins are found naturally. They're found in certain types of grasses and plants. They're used widely in the perfume industry, and they also have pharmaceutical value. Now, if you're looking at it saying, what is that? I don't even know what the structure is. Well, one isocoumarin is actually called warfarin. If you ever go to the pharmacy, if you ever get a drug from the drugstore, take out the box and take out that leaflet inside that has a structure written on it. It will actually give you the structure of the compound that you are about to take. Warfarin, this compound here, is actually a type of coumarin. It's used as an anticoagulant. It's used to prevent heart attacks, prevent blood clots in veins, arteries, and lungs. So these types of compounds do have pharmaceutical value. 4-hydroxymelion is actually a type of an isocoumarin, which is just a variation of coumarins. Isocoumarin derivatives exhibit a wide range of biological activities. They're thought to be antifungal, antitoxic, antimicrobial, anti-tumor reagents. So these could also be useful for pharmaceutical, in the pharmaceutical industry. The one that we're looking at is 4-hydroxymelion. And like I said before, this one has never been synthesized, but it has been found in nature. And in one instance, it's been found in brain-derived fungi. And in that type of fungi, it was found to have antimicrobial activity.
Well, just like to say, my name's Alan. That wasn't too obvious. And I would just like to point out that John had it easy, because when he was telling people about what he wanted to do for research, I mean, they might have mixed reactions, but I always got the same reaction. I was always like, what? So, the first thing to start off with is, how do we write out organic compounds? Because coumarins and isocoumarins and 4-hydroxymelions aren't just squiggles on the thing, it's just lines. So how we draw organic compounds is that we have carbons, hydrogens, and oxygens. And organic chemists are lazy. So they don't like to fit in the carbons because there's a lot of carbons in organic chemistry. We don't like to fit in hydrogens because there's a lot of hydrogens. So usually we chop everything out except for things that are reactive, like oxygens, nitrogens, and other stuff. So that's why there's just lines. We also use instruments. We didn't use too many books over the summer. So we had an HNMR machine, which is a proton nuclear magnetic resonance, which flips the protons. Exciting. What they can tell us about the proton is what they're next to, and what kind of reactivities are next to them. So you get different peaks telling you how many protons, what they're next to. We also use a GC mass spec, which is really two machines put into one. It's a gas chromatography and a mass spectroscopy. The GC part is a gas chromatography, which separates molecules according to polarity and weight. And then we have the mass spectroscopy part, which actually bombards it with electrons. That's kind of cool because it knocks off more electrons, and then the molecule can break apart. You can see what it's made of, see how large it is, simple stuff like that. That's what it looks like. Ooh, exactly. You can see the gas chromatography part over here and the mass spectroscopy part over here. And the thing is that this is actually in the organic lab. What you never want to do is touch it. Very fast. And this is what you get off of the GC mass spec. The top part is from the GC part. It's how long it takes to come off. Whenever you get a peak, that's when something's coming up. The bottom part is when it breaks apart. So right here, we have the molecular ion, which is usually the largest one. In this case, it probably isn't the largest one, and it's after a part of the molecule is already broken off. And from the bottom part, you can kind of piece together what came off, what kind of stuff you're looking at. So to make 4-hydroxymethylene, you have to start with something, and then you have to get there by a combination of different reactions. So the first one is we're going to put on a benzyl group on the alcohol. And then the second one is that we're going to iodinate it. The next step is to cyclize it. The fourth step is to hydroborate it, which means that we put on an alcohol group. And the last step is to remove the protecting group of the benzyl. So our first step is the benzylation. So we use benzyl chloride, salicylic acid, and sodium hydride. When we did this, we only wanted one thing. We wanted monosubstituted salicylic acid, which is C. Instead, we got A, B, and C, which is a disubstituted product, benzyl alcohol, and the monosubstituted product. So we thought, hey, benzyl chloride can do something. Benzyl iodide can maybe do it better. So we made benzyl iodide from benzyl chloride. And the thing they don't tell you about benzyl iodide is it's a tear gas. So it's always interesting when you come into lab in the morning and both of your teachers are outside crying. Those are exciting days. And so whenever we did this, since it was more reactive, we got the dye-substituted product, which is okay. And it is how we confirmed it. We did a GC mass spec of it, and we also did an HNMR. So down here, you can see that we have two singlets. The two singlets are the hydrogens right next to the benzyl group. And the top part shows that it's a pretty big molecule because it took about 26 minutes for it to come off the GC. And this is actually the one that we used for the sample. You see the 227. That's not actually the weight of the dye-substituted. It's the weight of the dye-substituted minus one of the benzyl groups. So, since we wanted the monosubstituted, we had to take off on those benzyl groups, which we did with a fairly decent yield. And this is the confirmation that we did indeed remove the benzyl group. And as you can see down the bottom, the HNMR changed. We only have one singlet now. And far to the left, we have what would correspond to the H on the carboxylic acid. And the molecular ion changed from 227 to 228, which is the weight of the monosubstituted molecule. So now we need to do an iodination reaction. And most of you are probably thinking, hey, you had the monosubstitute, buddy, just iodinate that. Well, it takes a long time. It takes a long time to dye-substitute it, and then take one of those benzyl groups off, and we had to run the GC mass spec, which took 30 or so minutes each time we had to do that. So while we were kind of running it, trying to figure out what we're doing, we decided to test what we're going to do. So we used 3 different compounds. We had to use benzoic acid, salicylic acid, and anisic acid. And you could be looking at looking at the procedure. We use like Tamida, S-butyllithium, THF, negative 78 degrees Celsius. Where did that come from? We actually did that by using dry ice and isopropyl alcohol. So yeah, we're dealing with some pretty cold stuff. It's pretty nasty. And here's the confirmation that we did iodinate the salicylic acid. The GC is on top, and the mass spec. And the 264 corresponds with the weight. And here's actually the benzyl part of the HNMR. And it kind of, you get the double peak because of how the iodine reacts to it, which is a good sign for us. And here's the confirmation of the iodinated anisic acid. And you can see GC mass spec in 278. The strange thing was, is while we were iodinating this, we got an unknown product that had a weight of 178. We weren't really sure what this was. We knew it wasn't an acid because whenever we cleaned it off, the compounds that we wanted, it left. So we knew it wasn't an acid. So then we tried to iodinate mono-substituted salicylic acid. And it did not work as well as we had hoped. There's too many competing sites because each of the benzyl group wants one of those iodines, and part that we actually wanted to bid on had 3 other additional sites. So we just got a jumble of stuff. So then we're like, well, that's not going to work so well. So we tried to cyclize the iodinated salicylic acid because we iodinated that pretty well, got a pretty good deal. So we had 2 different ways to do it. We had the traditional way, which is using more chemicals and stuff, and we had a green way, which used water as a solvent, which is usually unusual in organic chemistry and microwaves. So we had 2 different ways to do that. And we were trying to get what is underneath the X. We did not get that. We instead got what is underneath it, which is a reduced version of that. And that was kind of weird. There's a few possible explanations why this could be. It could be because we're using sodium hydride instead of sodium metal, and the hydrogen just reduced it. So our conclusions is that we were able to iodinate several carboxylic acids, which is pretty good. We performed cyclization reactions. And for future research, we could look into the mysterious 178, because even though that's not what we wanted to make, it's a very close to what we wanted to end up making, which is pretty good, and to complete the remaining steps of the synthesis. And I'd just like to acknowledge Dr. Gibson, Dr. Bryson, the CEM Corporation, and Shay Rogers. They're the people who do the microwave work. The Wingate University Department of Chemistry and Physics, and the Summer Research Grant. That's me working. Does anybody have any questions? Yes.
On the GC, when you had 2 peaks, is the 178 the first one? They came off and it looked like about 12. You had 2. There was 12 and a half, and then you had the product peak. Is the 178 one that's coming out about 12 and a half?
Yeah. So it came off early, so we knew it was light and it wasn't falling. Very favorable compared to carboxylic acid.
What are the benefits of completing the synthesis?
Well, it's just like the synthesis of any kind of drug. You can use it for pharmaceutical work. It has antimicrobial or antimicrobial products. So that's some stuff there. It's what keeps in the magic. No, wait, I'm sorry. Organic people don't do magic, we do voodoo. No, we had to do it under a nitrogen atmosphere, so we had to keep a balloon on it to make sure no air got into it because we needed it to be very dry. No humidity, which is pretty bad to do in the summer in North Carolina. Any more questions? Okay. Well, like Dr. Wingate said, there's a food outside, which I can't wait to get to. So, this is it.